Okay, so hello and welcome back. So basically what we want to do in this video is do a couple of exercises related to the concepts that we learned about functions. So basically the question that we have is example number 7 in the book. That you have, let A be the set of all 50 students of class 10 in a school. And let F a function from A to N be, and this N is basically the set of natural numbers, right? N be a function defined by f of x is equal to the roll number of the student x. Now we want to show that f is 1, 1 but not unto. Show f is 1, 1 but not unto. So now to remind ourselves of basically the concept of 1, 1 and unto. So we had basically three types of functions that we talked about in the previous video. We had the 1, 1 function. We had the many one function. And we also had the unto function. And also we said that if a function is 1, 1 and unto, if both of these are the case, then the function is going to be called a is going to be called 1, 1 and unto. There was also one other type which is called 1, 1 and unto, right? So basically 1, 1 and unto is called also bijective. 1, 1 and unto is also called bijective, and the 1, 1 function was called the injective. The 1, 1 was called the injective. And then basically we had many one and unto and so on and so forth. So what these functions are is that basically one by one, if I were to talk about them, I would say that basically a 1, 1 function is the type of function in the case of which the images of distinct elements of x under f are distinct. So the images of the distinct elements of x under f are distinct, meaning that, for example, suppose that you have 1, 2, 3 and 4 here. And suppose that you have basically A, B, C, D over here in another set, and it's called the set X, set Y. Now, if the images of distinct elements of X under F are distinct, meaning that this is, for example, related. This is mapped to this element is mapped to this element, this element over here, and this element here. You see that the images of distinct elements of X under F are distinct, meaning that it's not like, for example, the image of 1 is A and also the image of 2 is A. The image of 1 is A, the image of 2 is B, meaning that 1 and 2 being distinct elements of X, their images are also distinct. And for the same reason, definition wise, we call this a 1, 1 function. We call this a 1, 1 function, 1, 1, or injective. 1 1 or injective, right? Now if basically if the if basically the images of distinct elements of X under F are not distinct, then you call that a many one function, and that would be some situation like this. For example, 1 2 3 and 4, and you have A, B, C, and D over here in the other set. Let's say that this is set X and this is set Y. Now you can see that over here the image of 1 is A, the image of 2, let's say, is also A, and the image of 3 is B, and the image of 4 is C, right? So this is a many one function. This is a many one function, meaning that the images of distinct elements of X under F are not distinct, because the image of 1 is A, the image of 2 is also A, and these basically 1 and 2 are distinct elements of F, right? So that's many one and 1 1. There is another type of function which is called onto function, and an onto function is basically the type of function where every member of the set Y is an image of some element of the set X, right? Meaning that, for example, this is not an onto function, because this D is not an image of any elements of the set X. But then in this case you can say that this function is an onto function, because this is an onto function because let me read the definition over here. So we said that the function f from x to y is said to be onto or surjective, is said to be onto or surjective, if every element of y, is the image of some element of x under f, and that would be basically onto or surjective, right? Now and we said that also if a function is 1 1 and also onto, you can call that function onto, you can call that function 1 1 and onto, which is called a bijective. Right? Which is basically this exact function over here, meaning that the function is of course 1 1, it's also onto, so you can call it the 1 1 and onto function, which is also called the bijective, right? Now, the situation that we have here is that and let me actually make a screenshot here, because I'm going to most probably need these basically. I'm going to need this thing over here, and so okay, so now the situation that we have here is that what we are saying is that basically the set of all the students of all 50 students of class 10 in a school is basically the set A, meaning that you can imagine that the set A contains all of these 50 students, as for example John and David and Ashok and for example Rahul, and so on and so forth. and all the way up to the 50th student. All the way up to the 50th student, meaning that you can just keep going until, for example, you get to George, for example. Now, let's say that the roll number, let's say that we have basically actually sorted these students based on the roll number, meaning that the roll number of this student is 1, the roll number of this student is 2, 3, 4, and so on and so forth, all the way up to 50, and the roll number of George is 50. So I have this set of students here, which I can call the set A, and this set is mapped to the set of natural numbers. And basically, you have in the set of natural numbers, you have 1, 2, 3, 4, and all the way up to 50, and then 51, and then you can go all the way up to n. This is the set of natural numbers, right? So what that means is that, and the function f that we have defined here is that the roll number of the student f of x, basically the image that we have, the image of the elements of the set A, or f of x here, basically f of x, the image is equal to the roll number of the student x, meaning that if the roll number of the student is 1, then that element must be mapped to 1. If the roll number of the student is 2, then that must be mapped to 2. If 3, mapped to 3. If 4, mapped to 4. And so on and so forth until you get to the 50th student, right? Now, so as you can see, every distinct element of x, has a distinct image in every distinct element of A has a distinct image in n, based on what we can see here. And that's also based on the fact that no two students can have actually the same roll numbers, because actually that's not possible in a typical classroom. You don't give two different students the same roll numbers, because that would just that's just not possible in any educational setting. If you give two students the same roll number, then everything would be simply mixed up and messed up. So based on the fact that no two students can have the same roll numbers, then you will have then the situation is necessarily going to be such that every student is going to be mapped to every distinct student is going to be mapped to a distinct image in n, and so on and so forth, all the way up to the 50th student, which means that basically that the function f can be called basically f is, you can call it a 1-1 function, right? But the problem here is that in the set n, which is basically the codomain of your function, basically 1 through 50 you have no problems. But then after 50 you get, for example, the number 51. And as you can see, 51 is not the image of any element in A, which means that not all elements of n are images of some element in A, right? So basically, based on definition number 6, we said that the function f from x to y is said to be onto or surjective if every element of y is the image of some element of x under f. And as you can see, that is not the case here. 51, for example, at least this one number is not the image of some element of x under f. And so you can say that basically f is not onto or basically not surjective, meaning not surjective. So the way to remember these three basically terms that we had here. So first of all, we had the 1 1 function, which is also called an injection, right? Which is also called an injection. Then we had basically the idea of many one. We have the idea of many one function. We had no name for this, right? We have no other alternative name for this. And so, and then we had the type of function which was onto, which was called surjective, and there is also the type of function which is 1 1 and onto, which is called bijection, I suppose, right? Or bijective. So 1 1 is injection, and you can basically remember them based on these images as well. So as you can see, this is a 1 1 function, meaning that every distinct element of X has a distinct image in Y, and so you can call it an injection, meaning that every element here has been, well, I'm just giving you some sort of a simple way of remembering the words. They don't, I mean, the way that I'm saying it doesn't really make any logical sense, but just some way of remembering the words. So this is a 1 1 function, and meaning that every, you can imagine that every element here has been injected to a distinct image in the second function. So you can call that injective. Moreover, the second one, which is many one, doesn't have any alternative names. Onto is called surjective, meaning that you can see that no elements here have been left alone in Y. Every element of Y is basically the image of some element in X under F, and so since all the elements have been covered here, then you call it onto or surjective, right? I suppose I'm not making it any simpler for you, but, and then if the function is both 1 1, injective and both onto surjective, this exact same situation, then you can call it bijective, meaning that all the three words are actually related to the same image, and then many one, which is this image over here, doesn't actually have any names. So you have 1 1 injective, onto surjective, and 1 1 and onto bijective. And of course there is a good way to remember this, meaning that you can, since there is 1 1 and onto, there is 2 of them here, and there is bi here, meaning 2, then you can remember 1 1 and onto together becomes bijective, right? So that was that. So the next question that we have is question number 8, which is basically you want to show that the function f from n to n, you want to show that the function f from n to n given by f of x is equal to 2x is 1 1 but not onto. is 1 1 but not onto. Okay, so then basically what we have here is we have a function from n to n given by f of x is equal to 2x, and we want to show that this function is 1 1 but not onto. So 1 1 means basically as we argued before, as we mentioned before, 1 1 means injective, and onto means 1 1 means injection, is an injection, and onto means surjective, right? So then what we have here, so 1 1 is injection, and onto is surjective, right? So you want to show that basically f is an injection, which means a 1 1 function, but not onto, meaning that it's not surjective. Okay. Now, if I have a couple of values for this function, if I create a table of contents, a table of basically input outputs for this function, what I will have is that if x is if this is x and this is f of x, and since we are working with the set of natural numbers, we have 1, 2, 3, and so on and so forth. So 1 times 2, since f of x is equal to 2 times x, then 1 times 2 is equal to 2, 2 times 2 is equal to 4, 3 times 2 is equal to 6, and so on and so forth. That means that, as you can see, for example, if I have the set of natural numbers here, 1, 2, 3, 4, 5, all the way up to n, and let's assume that this is the set of natural numbers, and again, if I assume that this is the set of natural numbers 4, 5, and 6, and so on and so forth, all the way up to n, then what happens here is that basically 1 is mapped to 2, and 2 is mapped to 4, and 3 is mapped to 6, and so on and so forth. And what that means is that every element in the domain is mapped to, meaning that you can, as you can see here, shown by the ellipsis, you can say that every distinct element in the domain, every distinct element in the domain is mapped to a distinct element in the codomain, which means that, first of all, this is a function, and second of all, it is an injection, right? So this part is taken care of. But as you can see, there is a problem that, for example, 1 is basically 1 in the codomain. 1 is not the image of any element in the domain, or 3 is not the image of any element in the domain, or 5 is not the element of any is not the image of any element in the domain, and so on and so forth. That means that there is at least one element in the codomain that is not the image of some element in the domain, which means that basically meaning that the function is not surjective, right? So that's basically question number, or example number 8. So the solution here says that the function f is 1 1, for f of x1 is equal to f of x2, then 2 times x1 is equal to 2 times x2 implies that x1 is equal to x2. And further, if is not unto, as for 1 belonging to n, there does not exist any x in n such that f of x is equal to 2x is equal to 1. So let me write them down. It basically says that the function f is 1, 1. The function f is 1, 1. And of course it doesn't really, in case you cannot really remember those three terms, injective, of course it's not that hard. 1, 1 is simply injection, unto is surjective, and if it is 1, 1 and unto together, then it becomes bijective. So it's not that hard, but in case that confuses you, you really don't really need to learn those names unless it happens to appear in some context. So the function f is 1, 1 for f of x1. For f of x1 basically is equal to f of x2. That implies that basically x1 is equal to, that implies that 2x1 is equal to 2 times x2, which implies that x1 is equal to x2. This is the meaning of the same thing that I said, that every distinct element of the domain is mapped to a distinct element in the range, meaning that if f of x1 is equal to f of x2, that can only happen if x1 is equal to x2, meaning that if the x's are basically the same. So that means that no two different x's no two distinct x's can have basically no two distinct x's can have the same image in the codon, right? Now further f is not unto as for 1 belonging to n, there does not exist any x in n such that basically f of x is equal to 2 times x is equal to 1, which simply means that basically 1 is not the image of any elements of the domain of the function, right? Now, so this was basically the situation with f of x is equal to 2x, and we are here, as you can see, working with the set of natural numbers. And the set of natural numbers is basically this set over here, meaning that you have 0 and you have 1 and you have 2 and you have 3 and so on and so forth, all the way up to infinity. So what that means is that when you're working with the set of natural numbers, this is the set of natural numbers. When you're working with the set of natural numbers, then over here, you are simply assuming that there is no numbers here, right? Meaning that the set of natural numbers is simply, actually there is no 0 there. So over here, you're assuming that there is no numbers here. No number exists here. The set of natural numbers is simply 1, 2, 3, and so on and so forth, all the way up to infinity, right? So between 1 and 2, there is no numbers in the set of natural numbers, of course. And so the graph of this function would be something like this, meaning that you have 1 and 1, 2, and then this function, basically the graph of this function goes through the origin and this point here. So this is basically f of x is equal to 2x, and this is your y and this is your x, right? So as you can see, this is your domain. This line over here, this is your domain. This is your domain. And this line over here, this represents your codomain. This line over here, this represents your codomain. Now you can see that basically all the members of the domain, which are basically 1 and 2 and 3 and so on and so forth, 1, 2, 3 and 4, 1 is mapped to 2. And 2 is mapped to, for example, let's say that this is 4. And 3 is mapped to, for example, let's say this is, for example, 6. And 4 is mapped to, let's say, over here is mapped to, for example, 8 here, and so on and so forth, right? So, which means that basically all of these numbers here, and if I assume that this is, the set of, if I assume that this is the set of basically natural numbers again, and if I assume that again this is the set of natural numbers, then in the set of natural numbers I have this number over here which is 1, which is basically 2, which I'm sorry, 3 or 5, or and so on and so forth. So each of these elements, or any of these elements, is not an image of the, an image of any of the elements of the domain of the function. And so what that means is that then the function is 1, 1, but it's not onto. It is not onto, because these basically these members in the range or in the codomain are basically left out. Now suppose that you have the same situation. But now you're working in a different sets, or in two different sets. Meaning that suppose that you have some function f. This is by the way also example happens to be example number 9. This is example number 9. Suppose that you have this function f that goes from R to R, not from N to N, from R to R. So the set of, basically the set of real numbers is basically simply all the numbers that you might know. All the rational numbers and all the irrational numbers are the set of real numbers. And you know that basically you have the set of basically all the rational numbers, and you have all the irrational numbers. And what that means is that the set of rational numbers contains also basically the integers, and these integers also contain the whole numbers, and these whole numbers also contain the natural numbers. And so basically you have all the rational numbers here, and you have all the irrational numbers here. So irrational numbers would be some number like pi, for example, or the square root of 2. Rational numbers would be some number, for example, 2/5, and all the other kinds of numbers that you might know, for example, integers or whole numbers or natural numbers, and so on and so forth. So if you take all of these numbers together, that becomes the set of real numbers, which means that basically, which simply means that basically you're working with on a number line, and basically this basically this does of course include all the negative numbers as well. So you're going from 0 all the way up to 1, 2, 3, and so on and so forth, all the way up to positive infinity, and negative 1, negative 2, negative 3, all the way up to negative infinity. And since we are including all of these numbers in the set of real numbers, then that means that basically over here you also have the number 1/2, or over here you have the number 1/3, or over here you have the number, for example, I don't know, 1/5, for example, over here, and so on and so forth. That means that there is for example, you can imagine that between 0 and 1 alone, there is an infinite number of numbers between 0 and 1, and the same is the case with 1 and 2, meaning that between 1 and 2 again you have infinite number of numbers, and so on and so forth, going this way all the way up to infinity and all the way up to negative infinity. That means that all the numbers that you can think of are just simply included here, right? So which means that now if I have this kind of situation, and if I'm working with these two sets as my domain and codomain, what happens is that my codomain would be the exact same thing as the range of the function, meaning that no elements will be left out here. Every element here will be mapped to some element here, or you can say that every element here, each and every number on this number line will be the image of some element over here, and it's very simple to see, meaning that you would have, for example, the set basically x over here, which is of course the set of real numbers. Then you would have basically this axis over here, which is the y-axis. This is again the set of real numbers, right? And over here again we are saying that f of x is equal to 2x, right? So now if I draw the same function again, so 1 and 2 and 1 and 2, so f of x is equal to 2x again would be the same line. But now this time the function is 1, 1 and also onto, meaning that it is a bijection. So now as you can see here, you can imagine that there is all kinds of numbers along this line, and there is all kinds of numbers along this line, and all of these numbers are just simply, all of these numbers that you can find here are images of all of the numbers here under this function, meaning that, for example, you can say that you can pick any point here. For example, this point basically is a mapping from this element to this element. This point, any point that you pick would be this, would be the image of this element. This element would be over here. This would be the image of this element, and so on and so forth. That means that your function is 1, 1, 1, 1, and also onto. Now 1, 1 is an injection. I keep forgetting these three names. 1, 1 is injective, surjective. Okay. 1, 1 means injective, and onto means surjective. And since it's both injective and surjective, then you can also call it 1, 1 and onto, which is basically called a bijection. Right? Let's take a look at the solution here. So basically you want to prove that the function f from R to R given by f of x is equal to 2x is 1, 1 and onto. Okay. Now the solution that they have provided here is that it's usually beneficial to read those solutions, because there is these little things that you can learn from the solutions, right? Even if you have solved the problem on your own, it's beneficial to go through the solution. So as a solution, basically you can say that f is 1, 1. You can say that f is 1, 1 as f of x1 is equal to f of x2. That implies that 2 times x1 is equal to 2 times x2, which implies that x1 is equal to x2. So what that means is that there is actually that what this means is that basically all the distinct elements of the domain, all the distinct elements of the domain have distinct images in the range, right? Meaning that, and of course we have already talked about this. So now also given any real number y in R, also given any real number y in R, any real number y in R, there exists y divided by 2. There exists y divided by 2 in R such that f of y divided by 2 is equal to 2 times 2 times y divided by 2, which is equal to y. Hence f is onto. Hence f is onto. Now what that means, this part, okay, so basically this part, what it means is that let's understand this part before moving any further. So basically we said that, you know, that basically we are assuming that basically f of x, or basically this axis, we call it y, but this is actually nothing but f of x, right? So meaning that all the elements that you can find on this axis are actually images of x, right? So we are just simply calling them y. So if I assume that f of x is equal to y, then basically over here we said that f of x is equal to 2x, right? Over here we said that f of x is equal to 2x. F of x is equal to 2x. That means that now f of x is equal to y and f of x is equal to 2x. That basically means that 2x is equal to y, which means that x is equal to y divided by 2, right? So if instead of f of x, if I write y divided by 2, f of y divided by 2, that gives me basically, that gives me 2 times x, which is 2 times y divided by 2, which is equal to y. That means that, which is again the same thing, f of x is equal to y. So this is f of x, and this is of course y. So so that means that any y that you take here, that means that any y that you take here is, it says that given any real number y in R, given any real number y in R, there exists one y divided by 2 in R, such that f of y divided by 2 is equal to 2 times y divided by 2 is equal to y. That means that basically there is any y divided, any y in any basically y in R is the image of some element in the domain of the function, right? So that is basically example number 9. Now we have also number 10 and a couple more. So in the next video we will talk about example number 10. I'll see you in the next video.